Welcome back. We are still in session three in regard to scientific explorations. This session, which I might have to break up to a smaller components, is about the concluding remarks, the end results, how to make a conclusion at the end of the scientific exploration. Please do remember to change the setting on the YouTube recording where there is a circle. Make sure the setting is set to the highest quality. After 1 day of uploading the material on YouTube, you should be able to change the quality to maximum, which is HD. So that would make the writings that I'm going to show you a lot easier to see and follow. Let's go to the screen share, and I would like to refresh your memory about the early stages of our discussion, hypotheses, formation, and testing. So you have a null hypothesis, which is usually, generally, an accepted fact. For example, every person is innocent until proven guilty. And the water is going to boil at 100 degrees Celsius. So null hypothesis is so tested among thousands of years, decades of years, centuries of years, that nobody actually bothers to go and test them again. On the other hand, we have alternative hypotheses that is supposed to be mutually exclusive with H naught, H0 or H null. Sometimes it is called H1, sometimes it is called HA, A is standing for the letter alternative. This was an example, and it doesn't hurt to review that together, though smokers weigh the same as non-smoker. So the null hypothesis is the average weight does not differ. Whether a person is smoking or not smoking, you could potentially argue that the average weight is the same. The alternative hypothesis stated as HA is going to be the average weight is going to be different, okay? So if I wanted to test my null hypothesis is true and 100% confidence interval, that means fully confident that this is true, I need to actually go and sample 8 billion people on planet Earth. 8 billion people. Because I'm going to include smokers and I'm going to include non-smokers, and there's nobody else left, okay? So this is going to be 8 billion people. I can't do that, it's impossible. So instead of doing that, what we could potentially argue is that if from 8 billion people, if you take 2 separate samples, maybe 2,000 only, you see the big difference between 2,000 and 8 billion, 2,000 sample points, you could potentially say that one of the curve belongs to the smokers and one of the curve belongs to non-smokers. You take the average or the mean, you also take a look at the standard deviation, and the graph look very similar, perhaps exactly the same. Exact match of mean, exact match of the standard deviation would be terrific. And that might be actually quite too much to ask. But there may be just a slight, very insignificant difference between the two sets. That's why it is called null. Null means insignificant. Alternative hypothesis, on the other hand, says that the average weight is going to differ. So if you are smoking or non-smoking, the weight in this set is not going to be the same as this, and potentially there is going to be significant difference. So what do we do? In this case, we are going to take 2 samples, 2 separate samples, 2,000 again, and then we are going to observe its shape, the distribution, and mean, and then we realize that one of the curve is actually off compared to the other one in terms of mean. Maybe the standard deviation is the same, as you can see from this example, this graph, but the mean is off. So that's why you're going to say the alternative hypothesis has a bone, has a strings inside. Okay, we talked that the what was the normal distribution. Keep in mind that when we talk about sampling, the sampling could be done with different distributions. There are tons of different distribution functions and different sampling techniques, and they don't have to be the same. But we made two important observations in the last recording. One is that regardless of what the sampling technique is, or eventual population is going to look like, if you take the sample, say 2000, and take the average or the mean and plot it, take another 2000 and plot it, take another 2000 and plot the mean, put the mean in, and then take another 2000 and put the mean in, the mean of not normalized, normal distribution, normally distributed sample is eventually going to shape a normal distribution. So original sample, even the whole population, may not necessarily look a pure normal function. But when you start sampling and you take the mean and you put them in, and you put them in and put them in, eventually those means are going to actually look like a normal distribution. So that's one of the lessons we learned. Irrespective of the distribution of the sample or the population, if you take the samples and make this, say, hundreds of samples of 2000, for example, and the mean of that is going to shape a normal distribution. But generally speaking, not only that is an important discovery made a few decades ago, but also there is another aspect that you need to keep in mind, that majority of the events that are happening are not necessarily strange. They look like a normal distribution anyway. So this function is very important for us. And we need to actually take a look at this function and see what the function basically tells us. This is a mean, and in this case, the mean is 150. Most of the time, we actually shift that to the x-axis, make the mean 0. This is going to be 1 sigma, standard deviation, 1 sigma. So this is 1 sigma to the negative side, 1 sigma to the positive side. This is another sigma on this side. This is another sigma on this side. The length here is going to be 2 sigma minus 2 sigma, and this is going to be 2 sigma. We don't have a length, negative length. So it really doesn't matter, doesn't make sense for me to say minus 2 sigma. But this is to the left of the mean. So that's why we call it minus 2 sigma. And this is 2 sigma. And then we have 2.35, this third window for sigma, 2.35. And everything from minus infinity to this, if you add them up, is 2.5. If you add this and everything at the tail end on the right-hand side, that's 2.5. Let's review this one more time. So basically what we are talking about, a normal distribution that could be potentially a production of so many samples you have taken, and you have taken the mean and everything else, and you wanted to see how it looks like. So this is a normal distribution. If this is a null hypothesis, and this is supposed to be the most likely observation, when we say everybody, sorry, we don't want to say everybody, we want to say a person is innocent, it means that if you go randomly to anywhere on the planet Earth and you pick them up and you investigate the history and everything else, you realize that this person is innocent. May not be necessarily 100% bulletproof. There may be some speeding ticket, maybe some parking ticket, maybe some speeding ticket, but generally speaking, these people are decent and honest and just happen to have a mistake of getting a ticket for parking or something, right? Even if they have done it intentionally and they do have remorse, they regret it, right? Then this is going to be the area we were talking about, 2.5 and 2.5. 95% statistical significance actually comes from this edge to this edge. If you add everything underneath, and if you can return to the previous recording, this is going to be 95%. And 95% is really significant. So this is a 95%, we call that confidence interval. Now, when we say confidence interval is 95%, what is left? The whole area underneath, the area from minus infinity all the way to the peak, all the way to the plus infinity, if you take a look at the area here, it's going to be +1. +1 minus the 95% area is going to be 5%. And if you wanted to equally divide on the two tails, 5% divided by the 2 is going to give you 2.5%. That's what we mentioned in the previous slide, in this slide, okay? So this is going to be considered our critical, basically value, the critical value. And if you say, I want 95%, the critical value is going to stand at 5 divided by 2 for 2 tails, or you could potentially have 1 tail on each end, that would be 5%. Now, you might be very stubborn and you might be very picky and you want to actually make sure the significant or confidence interval is going to be 99%. Okay, if you're looking for 99%, your remaining basically area is going to be 1%. Now, if you have 2 tails, 1% divided by 2, that becomes 0.5% in each part. So 0.5% here, 0.5% there. And if you have 1 tail, again, refer to the previous recording, then we are talking about 1% total. Anyway, 95% is really good. So 2.5 is actually very important for us. And we would say that 2.5% here and 2.5% here are actually referring to very unlikely observation. It's very unlikely for you to go to the street and pick up someone by random and say, this person has abused the partner, or has killed somebody, or has stolen something, right? It's very unusual, very unlikely observation that's going to happen. So please remember that 0.5 divided by 2, that's 0.025, the 2 tail end. This is a general understanding. Keep in mind that this threshold, this critical value, could be set by you. So you could potentially say, listen, 2.5, it's too much. I want 1%. So if you say 1%, this would be 0.5, 0.5. You might loosen up a little bit if you want to, and that would be a bit strange if you do. You say, listen, I'm okay with 90%. If you say 90%, 10% is left. 10% divided by 2, that's 5%, 5%. So this critical value depends on how relaxed or how basically how important it is for you to have the confidence interval in this area. The normal distribution, as we spoke of, is actually a continuous function. This is a continuous function, which means all of the possibilities with all kind of decimals do exist, and it has a formula. And in this formula, as we stated last time, mu is the mean or the average, sigma is going to be the standard deviation, and pi is well known, 3.14, and e is 2.71. So we already know what the function is, okay? Now we said that we have, we are potentially looking at 2 curves here. One curve is H naught or H0. The other one is H1 or HA. This is in relation to null hypotheses, and this is in relationship to the alternative hypotheses. There are type 1 error and there are type 2 error, and I could potentially explain what these are quite briefly in the example that we have repeatedly utilized in this class. For example, if you pick up, if the judge said the person is innocent and the person is really innocent, so you see the person is innocent, you took them to court and the judge says this person is innocent. So there is no error. The person is innocent, the judge says innocent, and that's it. And the person is guilty and the judge found that person to be guilty. So when they say guilty, and that's really no error. This seems to be the justice system to be working perfectly fine. But then you have a person who is guilty goes to the court, and the judge, according to the procedures and laws and rules and regulations and all the precedences, says that this person is innocent. The person is guilty, but the judge says innocent. This is type 2 error. If the person is innocent, you take them to the court, and the judge, again, according to rules, regulations, all of the precedents and everything that this judge knows, says that this person is guilty. That's an error. You don't want this to be too big. You don't want this to be too big. This is not good for the system. You want this to be very good, and you want this to be very good. This is type 1 error, and this is type 2 error. We will talk about this table, which is called confusion matrix in a different recording. When you start sampling, you potentially could have a skewed basically distribution. So although the pool itself might be a normal distribution, but you might be leaning toward an area which is almost potentially all Republicans with a few Democrats, and then you might be leaning to another area which would be almost everybody is Democrats, but there are a few Republicans there. It would be nice to have basically normal distributions where mean and median are going to be basically the same. Now, in the so from now on, I'm going to make an assumption that we are not looking for different distributions. Bernoulli, general, Poisson, we are not looking for any other distribution at all. We're going to say that the experiment in front of us has a normal distribution. It's continuous, it's supposed to be continuous, but the reality is that when you sample, you are actually presenting discrete samples. And obviously, you're not necessarily, and I'm going to give you an example. So keep in mind that we may be facing with a non-continuous function at some point. Now, in order for me to basically find, if I have 350 million people in US, and if I start taking sample, and I know, for example, the 350 million people in US, according to the US Census, I'm going to know how many people, how many male exist, how many female exist, and how many identifying themselves in a different way. You exactly know what is the mean of the sample. You exactly know what is the standard deviation of the sample. Keep in mind, one of the assumptions we said is that the experiment we are running on a normal distribution. So that's one of the first assumptions. The second assumption we have made is that the deviation is homogeneous, meaning that you expect the, basically this deviation to be kind of divided, right? So you wanted this to be homogeneous. So keep in mind, we have mu and we have sigma. We know exactly the mu and sigma of original big size population of 350 million, of 8 billion on the planet Earth. If we do have access to that kind of a data, suppose that you have that mu and sigma is given to you. But because you are not going to go and sample everything, you're going to limit yourself to 2,000 people only, 3,000 people only, then you need to find your place onto the normal distribution curve. Remember, this was, if you remember, this was actually my sigma axis. The average was 0, and then you had +1 sigma, +2 sigma, +3 sigma, you had -1 sigma, you had -2 sigma, and you had -3 sigma. So that's how this curve was supposed to be known. And then what I need to find, if I have a sample, and in order for me to find a p-value, the p-value being, so if I wanted to go back to my original expression, on the p-value. So if I have critical value here, and if I say that the line is here, so the line is here, the area that I'm going to look into, that's going to be my p-value for that specific. So this is my critical value. So if I fall here, everything on the area on the right-hand side and on the area on the left-hand side, together, that would be constructing my p-value. The p-value hopefully is going to be less than 0.5 or 5%. So in this case, if the critical value is different, then of course it's going to change. But the p-value is supposed to be less than, I want to understand what the p-value is. I want to calculate what the p-value is, okay? So the way I do it, considering, so here are our assumptions. We know exactly what the mu of the population is. We know exactly what the sigma of the population is. But we don't have access to the entire population because I'm not government. Government can have mu and sigma, but I'm not government. I'm just somebody outside. I'm trying to do a sample. And I go and have 2,000 people taken. And I want to have these 2,000 people, and I'm going to repeat that as you remember. So for me to find my p-value, the way I'm going to do it, I first need to place my number on the x-axis. On the x-axis, you had 1 sigma, you had 2 sigma, you had 3 sigma, minus 1 sigma, minus 2 sigma, minus 3 sigma. So I need to do that. So in order for me to do that, I just need to find the z0. When I say z0, it's going to be number because I'm actually dividing this. If it was the normal distribution of the entire population, I would divide it by sigma. So when you take a look at the curve, you see +1, +2, +3, -1, -2, -3. So you see, there is no sigma. I divided it by sigma. Now, since my sample is only 2,000, I need to actually divide it by sigma over a square root of n being my sample size. So what I'm going to do, I'm going to take the basically the mean of my sample minus of the mean of the population divided by the sigma of the population divided by a square root of n. So with this formula, I'm going to see exactly where my z is. Now, if I have left tail, right tail, and two tail, what happens? In the left tail, I want my z to be less than z0 in order to calculate the p-value. So this is my critical value. We didn't say 0.5. It could be anything you choose. And for that in mind, I'm going to have my z to be less than z0. Agreed? Make sense? So this is going to be, so this area, anything here, less than z0. And if I find the probability, remember this is a probability function. Its maximum can never exceed 1, can never exceed 1. It's usually a lot less than that, right? But it can never exceed 1. The entire area, when I add them up, must be 1. The entire area is 1. So what is the p-value? The p-value is the probability of the z less than critical value z0. That's left tail. If I do it on the right tail, the probability of z greater than z0 will be my p-value. If I do it as a two-tail, what I'm going to do, I'm going to divide them. So I'm going to say z less than minus critical value, or z greater than z0 as in critical value. And I want to see what is happening on this side, what is happening on this side. But generally speaking, since the system, the curve, is actually symmetric, I don't have to calculate both. I just need to calculate one of them and multiply it by 2. So this is the way we calculate p-value if the continuous function is given to us, okay? This is another example. For example, I want to calculate the z. I have an experiment. In this experiment, I happen to have 198.67, an exact mean of my population, my solution space, and the standard deviation is 41.31. So where is going to be my z? 100 minus the mean divided by the standard deviation. And this is for the entire solution space. It's for entire solution space. So that's why I didn't divide it by a square root of n, because I'm not talking about a small sample. I'm talking about the entire solution space. An entire solution space, I have already taken that into account in calculating the mean, in calculating my standard deviation. That's a totally different story. I already calculated the 350 million here and the 350 million here. It's already there. So I don't have to redo it, okay? But let's take a look at an example. Test the claim that the true mean of number of TV sets in US home is equal to 3, which means if you pick up any home, potentially there are 3 TV sets. Let's assume that sigma, the standard deviation, is 0.8. And I said the US home is equal to 3. So I'm actually saying the mean, the true mean of the entire 350 million people, and you need to take a look at the household. So we are talking about homes, and maybe it's no longer, so you could say divided by 3, maybe on average. I'm just trying to make up some numbers. So how many houses do we have? Maybe 110, 120 million houses. We are saying that the mean of number of TV is 3, and the standard deviation is 0.8. We already aim for it. State the appropriate null and alternative hypotheses. So mu is 3, and HA or H1 is simply exclusive, mutually exclusive. So anything that is not 3, that's going to be not equal to 3. And because I'm actually looking at 1, 2, and 0, 4 and 5 and 6 and 7 and 10, I'm looking at the two sides of the curve. So this is a two-tailed test. Specify the desired level of significance. I'm going to say alpha is equal to 0.05, which is 5%. And that means my confidence level is 95%. So alpha is 0.05 or 5%. Choose a sample size now. I'm not going to knock every home in US and then ask them how many TV sets do you have. I'm just going to go and start doing some samples. I'm going to take 100 homes in my study. And determine the appropriate technique. In this case, we are doing a Z-test, very simple. The population is so big, 350 million divided by 3 as membership of a house, 110 million and 120, that a Z-test is going to be sufficient. So set up the critical value, we already did. The critical Z values are, for this one, is going to be, considering the sigma we have, it's going to be plus minus 1.96. Collect the data and compute the test statistics. So we go and we have 100, and we have the mean 2.84. It's no longer 3. It's no longer 3. And the sigma 0.8 is assumed known. So we didn't even argue with that. Let's say that the standard deviation is actually homogeneous. So because I have a smaller sample, I need to divide it by a square root of n. So that's why the 100 square root of 100 comes in, and my z becomes -2. Agreed? Now let's take a look at this. So I'm going to see what my probability is. So z less than -2, so this is -2, and this is +2. As we said, this is a two-tailed test. This is -2, this is +2. I'm going to calculate the probability using many tools available. I have a function. I can potentially use that function to calculate that. And remember, in that function, I'm actually putting the true mean and the true standard deviation. So that's the big difference. I'm putting the true mean and true standard deviation in my function. If you remember my function was, I believe, this one. Here is the true mean and true standard deviation, okay? So when I do that, I can potentially calculate and take the area underneath. So it's not just a function, it's not just the envelope, it's the area underneath. And then you find the p-value for the left to be 0.0228, on the right 0.228, and the total is 0.0456. Now, you could either do the integration and calculate the area underneath. There are ways of doing that using the tables. And tables were used before computers came to life, and people were using tables simply to find the p-value. I might have some link to show you how they did it anyway. Reject H naught if Z is less than -1.96 or Z greater than 1.96. Otherwise, do not reject H naught. But in this case, it is. It is less than -1.96, and therefore we are going to reject the null hypotheses, okay? We did that already. So that's what so there is sufficient evidence that the mean number of TVs in US homes is not equal to 3. It's not equal to 3, but means there are sufficient reason to suspect that there are basically more or less TB sets at this time because we did a two-tailed test. Now, once again, if you know exactly what mu is and S or sigma is for the population set, for the solution space set, for the biggest possible set, 350 million people, 120 million household, 8 billion people, whatever it is. If you already know that, you could potentially conduct this, and it is called this is going to help you to find the probability. Now, what happens if the experiment is not referring to it's not going to be necessarily referring to a continuous signal. Now, if you take a look at this, I'm flipping a fair coin. I know from my knowledge that if I flip the fair coin, I'm supposed to get, for example, 50% of the time. If I do that billions of time, I'm supposed to get 50% head and 50% tail. So what happens if you don't have the function to be continuous? Here you have on the horizontal axis number of heads in a 30 flip. So my sample is 30. So it's going to be 30 flip from 0. I didn't try anything up to 30. Very unusual that in 30 flips you're not going to get basically any head, for example, right? So I'm going to actually calculate basically the frequency of the incident, and I'm going to plot them as a curve, as a discrete curve. Now, if this is the case, your question would be, how can I use the p-value formula? All you have to do is to actually calculate the area. So this one is area. This area is actually the length times the height, plus 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 the length times the height. So you could potentially calculate this area. If it is important to you, you can actually calculate the area. Remember that you have already calculated, although this is discrete, you have already calculated all of the areas, the small little bars. This is a bar chart, and small little bars, and the area is simple. You can calculate that. Now, you can calculate the area equally on the other side. Hopefully, it is going to be a match in terms of symmetrics. Maybe it is going to be a match, maybe it is not, but close enough. So what happens is that you're going to calculate these, you're going to calculate these. It's an area, it's a square area. Just sum them up. And then you have the total square area. And what happens is that you're going to tell me what the probability is. So the probability is here, it's going to be 0.03, 0.03. You could potentially argue in the sample that you're looking at 0.06. If your critical edge, if your critical value, if your threshold was 0.05, then you're exceeding that. So the fact that this is basically not a continuous function should not necessarily scare you, okay? It is very easy to calculate p-value now, having Excel file, having programming languages, including in Python. In an example we will be running, you will see it's just a simple command now available from a library. You could potentially calculate the p-value, and in this case is almost 0. This one is almost 0, okay? I'm just showing you an example. Now, one thing you need to keep in mind, that if you happen to have the complete information about the population, 350 million, 8 billion people on planet Earth, then you could potentially calculate the sigma or sigma to the power of 2 using x minus true mean divided by the sample, 350 million. So this is to the power of 2, you sum them up, divided by n. So this is understood. This is understood. What if you don't have the true mean? What if you don't have the true standard deviation? What if you're talking about something that US Census data is not available? What if you want to take a look, I don't know, for example, how many, it's very hard to come up with the data that is not in US Census. You have eye, color of eye, and all of that is recorded. As far as I understood, you have height usually is recorded. I'm not sure if weight is there. You have education perhaps is there, right? But you could potentially have something that is not available to you, as in the biggest, the most comprehensive population or sample solution, or a solution space, sorry, solution space. So what do you do? In that case, you are looking at the sample that you have taken. Still, it could be 2000, but you don't know the true mean. You don't know the true standard deviation. What you could do, you could actually calculate the mean anyway. The mean is simple. You're going to add them up and divide by the size of the sample. So x1 plus x2 plus x3 plus x100 in the previous example, divided by 100, that's going to be your mean. So the mean is easy to find. But since I'm finding the mean, I'm actually looking at the data that has one extra piece of information, and that is the mean. Remember, I said, so let me try this one. X1 is 5. X2 is, let's make a better number. X1 is 4, and X2 is 6. Just two numbers, two samples. What do you do? 4 and 6. What's the average? 4 plus 6 is 10 divided by 2. 4, 6 plus, you divide by 2, that's going to be 5. The average of a sample 4 and 6 is going to be 5. You understand that? But if I ask you how much information do you have, you're going to say, okay, I have 4 and 6 and 5. Why did you give me 5? You can say I have 4 and 5 as an average. Yes, you can. You can say 6 and 5 as in average. Yes, you can. You can say 4 and 6 as in sample data. Yes, you can. You don't need to give me all three numbers. You don't need to give me 4 and then 6 and then mean. By bringing mean into the system, you actually have duplicated some of the information that exists in the system, in the sample. So what we are going to do, we are going to actually be very conscious about it. In that process, by looking at the sample mean, it is enough, and I'm going to take one of the data out. One of the data out. So if you take a look at my standard deviation, it's going to be all of the 4 minus 5 plus to the power of 2 plus 6 minus 5 to the power of 2. So that's what I did, divided by basically 2 minus 1. Because I only need one of the sample data and I need the mean. I already have the mean. I calculated the mean. 4 plus 6 divided by 2, that's 5. Right? I already have the mean. The mean is here. 5 is here. So if you have 5, this is called degree of freedom. This is degree of freedom. So let's try something else. Suppose you have 3, 7, and 10. I just wanted to have some nice number. 3, 7, and 10. 3 and 7 and 10. 3 and 7, 10 plus 10, 20 divided by 2. That's going to be 10. So the average of 3, 7, divided by 3. So I want a better number. So 3, 7 is 10, and I want to make it 11. Okay, so 3, 7, and 11. 3 and 7 is 10. 10 plus 11 is 21. Then you need to divide it by 3. So what do we get? You get 7. So basically, you're going to say that the mean is 7. Now, if you take a look at this, 3 minus 7 to the power of 2 plus 7 minus 7 to the power of 2 plus 11 minus 7 to the power of 2 divided by 3 minus 1. Because you already have adequate information inside the mean that you exactly took from the sample. Here, though, you are talking about X of sample. And this is the true mean. The true mean does not exist in your sample. You didn't get the true mean out of your sample of 100. You remember that? You didn't get the true mean out of the sample of 100. The true mean came from 350 million. That's why you have to have n. This n belongs to x. You are not duplicating information here, but here you are duplicating information. So if I don't know my average, the true mean, if I don't know my standard deviation, then your standard deviation needs to be divided by n minus 1. And n minus 1 is called, sorry, S2, I'm saying, divided by n minus 1 is called a degree of basically freedom. And then you take the square root, and that becomes the standard deviation. This is called sample variance. This is called variance for sample, and this is called a standard deviation, okay? It's easy to calculate these, as I said. Remember, if the number of samples go up, how do you calculate this? It's really easy in Excel file to actually have x minus y easily, x minus y to the power of 2 easily. You can actually calculate them and sum them up. So this is the sum. I just want to show you that it is very easy to do in Excel file. You really don't need necessarily to have the basically the Python coding skill. Now, I'm going to stop and I'm going to continue my rest of the argument in the shorter recording after this. Thank you.